Welcome to The Explainer. Today, we're going to talk about a word that you hear everywhere, resilience. But we're not just going to treat it like a buzzword. We're going to dive into what it really means, how systems, whether that's an ecosystem or our own communities, actually manage to survive when things get tough. So let's start with the big question, right? When a major shock hits, a huge storm, a long drought, even a financial crisis, why is it that some systems just completely shatter, while others seem to bend with the pressure and find a way to keep going? This is the core puzzle that the science of resilience is trying to solve. And to figure that out, here's our roadmap for today. We'll start by looking at stability versus resilience. They're not the same thing. Then we'll get into the anatomy of resilience, what it's made of. After that, we'll put it to the test with a huge real-world example, climate change. And finally, we'll look at how we can actually measure all this stuff. All right, first up, let's draw a really important line in the sand. We tend to use stability and resilience like they mean the same thing. But in the world of system science, they describe two totally different strategies for survival. And honestly, getting this difference is everything. Okay, so a stable system is all about bouncing back to exactly how things were before. Think of it like one of those old Weeble Wobble toys, right? You push it, and it pops right back up to its starting position. An irrigation ditch that handles a quick rainstorm and then goes right back to normal flow, that's a stable system. It's designed to handle small, predictable bumps in the road. Resilience, on the other hand, is about adapting to survive. A resilient system can take a much bigger punch. Now, it might not go back to being exactly the same, but it keeps its main job going. So take that water system again. If it's faced with a massive flood, a resilient one might actually change its own structure to become a retention pond. It's still managing water, its core function, but it's doing it in a whole new way. It literally bends so it doesn't break. So here's the bottom line. Stability is all about snapping back to how you were. Resilience is about finding a way to keep doing what you do. A stable system is rigid. It tries to preserve its form. A resilient system is flexible. It's willing to change its form to preserve its function. Okay, so if resilience is this amazing, flexible superpower, then what are its building blocks? What does a system actually need to have in its DNA to be resilient? Let's pop the hood and take a look. Well, it turns out resilience isn't just some vague, magical quality. It actually comes from a few key design features. We're talking about things like redundancy and diversity, modularity, smart feedback loops, and having decentralized control. So let's break each of those down. First up, redundancy and diversity. This is really just about having backups, and not just one backup, but different kinds of backups. It means you have multiple ways to get a critical job done. A city with several different water sources or a bunch of different emergency routes is way more resilient than one that depends on a single pipeline or a single bridge. If one part goes down, no big deal. The others can pick up the slack. Next is modularity. And the best way to think about this is like the watertight compartments on a ship. If one compartment gets a hole and floods, the bulkheads seal it off, the damage is contained, and the rest of the ship stays afloat. A modular system is just like that. It's built in these separate but connected parts, so when one part fails, it doesn't create this horrible domino effect that takes the whole system down with it. And third, resilient systems have these awesome adaptive feedback loops. This is how they self-regulate. They're constantly taking in information about what's going on, that's the feedback, and they use that info to make adjustments. A really good negative feedback loop works kind of like the thermostat in your house. It senses when things are getting too far off track, and it pulls the system back toward balance before it spirals out of control. Okay, so we've got the theory down. Now let's apply it to what is maybe the biggest resilience test our entire planet has ever had to face: a changing climate. So how do we actually build communities that can handle more extreme weather and not just break? Well, the science gives us a pretty clear roadmap, and it's built on 5 big pillars. And you'll notice how these tie right back to what we just talked about. You've got flexible infrastructure, that's modularity. Then there's diversity of livelihoods and resources, that's our redundancy. You also see community participation and strong networks, which helps create that decentralized control. And finally, knowledge and learning. What's that? Well, that's what creates those adaptive feedback loops, letting a community learn and get better over time. And that brings us to our last section. And for me, this is where it gets really powerful. For a long time, resilience felt, well, it felt like a nice idea, a philosophy. But what's so cool is that we now have the scientific tools to actually measure it, to model it, and to design for it. So, a huge insight here is figuring out a system's resilience threshold. This is its tipping point. How big of a shock can this system take before it either collapses or, maybe worse, gets flipped into a totally new state that you really don't want? Scientists call that new state a different basin of attraction. So, being resilient means having a really deep, wide basin, which makes it super hard to get knocked out of your good zone. And get this is not just guesswork. Scientists have an amazing toolkit now to actually put numbers on resilience. They can use things like system dynamics to model exactly how long it takes to recover from a shock. They use network analysis to hunt for those dangerous single points of failure we talked about. And with something called bifurcation analysis, they can even predict the precise point where a system might just suddenly and catastrophically fall apart. And this quote, I think, just nails the whole idea. Resilience is not about building systems that are invincible, that never fall down. That's impossible. It's about building systems so that when they do get hit, and they will, they can absorb it, learn from it, and get back up, often even faster and stronger than they were before. So we'll leave you with this final thought. The science here isn't just for describing what happened in the past. It's for predicting and building a better future. We have the tools. We can engineer resilience. So the question for all of us isn't, can we do it anymore? It's how will we choose to build it into our communities, our infrastructure, and our shared future. Thanks for joining us on The Explainer.